Okay, so welcome everyone. This will be our first collective meeting for the QCourse551. As you know, we had some difficulties and we're still, let's say, trying to solve some issues. But anyway, with green projects, we will start today. Currently, 2 green projects cancelled. And hopefully we will be able to offer new projects to them. I mean, some of maybe they will join the existing project. And also Gibran proposing a project. I hope we can cover all these students. Our aim was make 2 sessions because there were a lot of groups, etc. But now we have only 4 projects. So 8 groups in total it should be, and we decided to make a single session. So each group should present their progress, and your judges will be me and Gibran. Okay. Original plan was maybe there can be judges from also classic side, but currently we will just go from keyword side. Before starting, do you have any question? Can write in the chat or just raise your hand. Okay. Each group should have a easy name, like easy to remember and short name. And today I will also collect these names. Okay. We will start with 32, and who will present? I should also give right to.
My group will be going first.
Yeah. 32. I need one project from 32.
Yeah. I'm from project 32, and I think we can go first if that's okay.
What is the name of your group?
32. Terry QPE. I can share the slide. The slides
yes,
of the
yes,
name.
it is.
Yeah. Oh, share screen. Give me a moment. Sorry.
There are questions. Can project 31 group B continue the project independently? What do you mean, David? How you continue independently?
Oh, sorry. I'll need to reopen my Zoom. I'm so sorry about this.
Okay. And meanwhile, I can answer the questions.
Oh, wait. Is it sharing the screen?
Yep. We are seeing. David, can you explain, please, what do you mean independently? We can do ourselves with limited help. I don't know. We should check this. I mean, somebody should evaluate your progress reports. There should be mentor anyway. So, but let's consider this. Can you write me in Slack? Who are these people? And also canceled projects can present today at the end if they have something to present. We can continue, but we should find a mentor anyway. So you are theory QPA. I am.
Yeah. Should I start presenting?
Yes, you can start. We have up to 8 minutes. Thank you.
Okay, so I am Seamin and my group mates are Aditya and Christian. We are under the project 32, and we are doing smart post-processing for algorithms with QPE. Our group name is Theory QPE. And the reason for our group name is that we intend to improve QPE post-processing through theoretical methods. As a short introduction for each of us, I'm a physics undergrad at the National University of Singapore. I was formerly a research intern at A-Star where I did modeling trees using computer graphics. I'm also a quantum enthusiast and I love cats and the night sky. Does Aditya want to go next?
Hello, my name is Aditya, and I'm currently pursuing artificial intelligence and data science as a major. I'm currently working with startups in my country in areas such as quantum finance, but I'm currently shifting more towards the theoretical aspects. I'm building also my startup in neuroscience, and I also love movies, among other things.
Hello, can you hear me?
Yeah, we can hear you.
Yeah, we can hear you. Okay, my name is Christian Sousa. I am a theoretical physicist. I'm currently working as a professor at the University of Córdoba here in Colombia. And now I'm father of 3 girls. So my life is a little entangled one. And I love to do CrossFit. Go ahead. So basically, we all have some homework these 2 weeks. So one individual and group homeworks. So we, this next slide. We were dealing with the math behind the quantum phase estimation protocol in 2 cases. The basis case, in which the target state encode only one phase, in which we computed the probability to get to estimate the phase in terms of the number of qubits in the control, let's say, register. And after making the quantum Fourier transform, the inverse of quantum Fourier transform, we compute the probability in terms of the outcome results for the final state to get this phase here. So this is an example for one single phase. And the second homework was to compute the general case. I mean, when more than one phase is taken into account in the initial state. So these A sub k are the amplitude of this superposition, and we computed some examples to the phase estimation with, in this case, 3 different phases, in which you can see that the peaks of the probability after measuring the final state goes around the selected or the choose phases. And also we had a group homework to make a Python project in which we are computing the probability for an input set of amplitudes, let's say amplitude for the initial state, and different phases. We are dealing with the computation of the density matrix of the final state. Thanks.
Based upon our learning so far, we have the proposal of our end article to be a project based upon enhanced approach to outperform the existing solutions. The paper of interest for this project is one by Yifeng Xiong, which basically enumerates that QPE currently suffers from spectral leakage. The reciprocal of the record length is not an integer multiple of the unknown phase. This in effect reduces accuracy. To address this issue, the paper proposes a dual frequency estimator that asymptomatically approaches the Kramer-Rao bound when multiple samples are available. Numerical results demonstrate that this estimator outperforms existing window-based methods and the number of samples is sufficiently high. Based upon these readings, our objectives for our end article is to perform a theoretical analysis of a solution to a problem using the Kramer-Rao lower bound, CRLB, based upon the Fisher information. The CRLB is a lower bound on the variance of any unbalanced estimator of a parameter, and it can be used to assess the performance of different estimation methods. And in the end, we intend to improve the solution based upon the theoretical analysis, then demonstrate the improved solution on a real-world problem, and compared the improved solution to the solution presented earlier in the article Dual frequency quantum phase estimation mitigates the spectral leakage of quantum algorithms by Yifeng Xiong, and that reduces the approximations to improve accuracy without increase in computational costs in the earlier article, and show that the improved solution is far better on the same examined parameters. Thank you. We thank the judges and the jury and all the audience for listening to our presentation, and currently open the floor to welcome any inquiries or comments from the audience.
Okay, how you would classic platform?
Could you repeat that question a bit?
Indeed, your theory group, will you use classic platform or not?
We will be using the classic platform. But right now, in fact, in one of our homework, we already used the classic SDK to implement the QPE, and we'll be like working on the post-processing with that.
Okay.
Okay.
So even if you are theory group, you will also do some, let's say, implementation on classic platform, correct?
Yeah,
Yes,
we intend.
because actually, yes, because this may involve developing new algorithms, improving the existing algorithms, or optimizing the parameters of those algorithms. So this can be done by implementing the solution in a software or hardware system and testing it on the real world data. For that, we will be using the Classics platform.
Okay, okay. I have just a small comment. It's not good practice to read the slide like, okay, it's better maybe on the slide short items, and then you can use more wording. Gibran, do you have any question?
No, not right now. Thank you.
And from audience, any question, comments, remark? Okay, thanks. Maybe second group from 32 prepare. I think David has a question, if I remember.
I will introduce second part of this project.
Yeah. Okay, Yasim, just give me 1 minute. I will just reply. I think David asked. David, I will ask mentors. I cannot say Amir can be mentor. I think he's also like has some management role. I am not sure he has time, but we can. I mean, if your group is ready with limited help, and if you already done some progress, maybe we can consider this an option. As I said, please write me all these people in your group, also in the Slack, and I will check with the mentors. Sorry, Yasemin, you can share now and start.
Okay.
Your group name?
Application QPA. QPE.
App QPA.
Application QPE.
Okay, I will shorten it, App QPA. Thank you.
Application. Can I start?
Yes, please.
Hi, my name is Yasemin. Our project is smart post-processing for algorithm with quantum fast estimation. I will present application part of this project. Our group name is Application QPE. Our group members are Viraj, me, and Tonmay, Pikam, and Junior. And our presentation ingredients are forms are introduction, background, objective, theoretical highlights, computational and graphical analysis, conclusion, and future works, and reference. I will introduce. We will present. Quantum fast estimation algorithm is one of the most important applications in quantum computing world. frequently used as a subroutine in other quantum algorithms such as Shor algorithm. Suppose that there is an equation like that, and U is the unitary matrix, and U is eigenstate of this operator, unitary operator, and exponential term is the eigenvalue of these unitary matrices. The goal of the false estimation algorithm is to estimate the false and essential ingredient of the quantum false estimation algorithm, inverse of the quantum Fourier transform, and controlled U gates are given by like that. Circuit of the QPA is like that. This circuit is formed by two registers. First of all, first register is n qubits, and second is depend on the state. And after we apply Hadamard gates, and then we are applying control U gates, and after that we are applying inverse of the QFT, and finally we are measuring. And objective of this project, understand the mathematical theory underpinning QPA and implement it for some cases. Traditional methods, circuit depth grows exponentially with the desired precision of the path. Improve the result with the classic platform, enhance the result using substantially less data. Explore application such as finance-related scenario as a practical examples. Explore its applicability in diverse domains like chemistry, encryption, and other potential student-generated ideas. And,
Yeah, hi everyone. My name is Viraj. So I'll quickly go into the mathematical development behind this quantum phase estimation. We start first with a single state psi. So if we have a unitary operator acting on psi, which gives an eigenvalue e to the power 2 pi I theta. So we are interested in estimating the value of theta. So this psi goes into the target register of the QPS circuit that was shown earlier, and on the control part we have n number of qubits, and this n is represented as t in this equation. So, and the number of qubits t taken will be dependent on how precise the value of theta we need. So once we load this particular state and all the state psi and all the zero qubits in the QPE circuit, we get this particular result phi 3. Phi 3 is basically the state which is observed which is observed after the QP after the state after the QP is implemented on the state 0 psi. So this is the state we get, and you can see in this particular state that the term in the bracket y divided by 2 power theta 2 power t minus theta by 2 pi, when this term becomes 0, then the probability of measuring a given y becomes 1. So the general expression for the probability of measuring a given y is given in, we all have calculated this theoretical expression. It's given by this expression which you see on the slides, and this particular probability tends to 1 when the term in the bracket. That's why minus theta m by 2 pi becomes 0, and that's the state. That's the theta we can calculate once we once we look at the graphs for the y for which the probability becomes 1. So this is the case for the single state system. And now we look at the case of superposition, and psi is not a single state but a superposition of several eigenstates of U. So this is the superposed state, that's sigma ak. Just a minute. Sigma ak psi k, that's the superposition state. And now we are interested in calculating the phases associated with each of the states in the superposition. That's given by theta k. We do the same thing. We load this particular state into the QP circuit, and and the final state after implementing the quantum phase estimation algorithm turns out to be this expression, and probability of measuring a given y0 is given in terms of the expression that you can see on the slides. And here we see that the probability of measuring given y0 is not exactly 1. The only difference between this expression and the expression in the previous slide is this term sigma a square that comes from the amplitude of the amplitude corresponding to a given cycle. And this expression, you can see that it peaks for multiple values of y, which will be clear from the visualization that will be presented next.
Hi,
Viraj,
I'm Tanmay Nandi.
we have some problem. Okay, Viraj finished?
Yes, I
Yes,
finished the
yes.
theoretical highlights.
Okay.
Now the graphical part will be shown.
Okay.
Okay, this is for the graphical analysis. We'll get the probability function for single eigenstate and for the multiple eigenstates case. In this, this is the graph for single eigenstate case. This is plot of probability function as a function of y. And so basically, we have taken a single state with whose phase is 3 pi by 4, and we have varied the value of y from 0 to 8, 0 to 7, and the value produces basically for the value of 3. When y is 3, the value matches the theta value, theta m divided by 2 pi value, and this produces a peak at the point y equals to 3. Other than that, other points, the probability function becomes close to 0. That is why we are getting only one peak around y equals to 3, and at other points it is close to 0. And the right side is basically plot for different theta like 0, pi by 4, 3 pi by 4, 2 pi by 4, these functions, these phases, and this plot basically produces peaks at y equals to 0, y equals to 1, y equals to 2. And in the next case, go to the next slide. So this is the multiple eigenstate case where we have taken two eigenstate with phases pi by 4 and pi, and basically it produces two. Since there are two eigenstate with two different phases, it will produce two peaks at corresponding y value, which matches with theta k m divided by 2 pi values. So the height of the peak depends on the coefficient ak of the eigenstate, and in this case, in the left case, we can see that both of the peaks are same height at 0.1. It is because the ak, the coefficient, is basically 1 by root 2, and the square in the formula we can see the square. There is a ak square term which basically gives 1 by half. For both of these cases, pi by 4 and pi, we get a peak at y equals to 1 and y equals to 4 with a peak height of 0.5, basically half. And on the right case, we have chosen the ak value to be 1 by root 3 and root over of 2 by 3, which produces the graph for pi by 4 at a height of 0.33, which is basically 1 by 3 value. And also for the pi case, we get a peak at y equals to 4 with a height of 2 by 3. That is the case of graphical analysis. Now Junior will present the next case.
Hello everyone, I'm Junior Tajige and I present the the how been done so far with quantum phase estimator. Firstly, we have full mathematical development of QPE for single and multi eigenstate case. We stored Python program for probability function and density matrix function, and future work plan, we implement a single eigenstate case using classic SDK and read paper for exploring application and QPE in financial case. We can also have quantum cryptography application. Quantum phase estimation can be used in quantum cryptography protocols such as quantum key distribution. Quantum key distribution protocol rely on the principle of quantum mechanics. to secure the transmission of encryption keys. We can apply in quantum optimization. Quantum phase estimation is a crucial component in quantum optimization algorithms, such as quantum approximator or quantum algorithm. It's designed to solve combination optimized problem by employing a combination of classical and quantum techniques.
Sorry, Junior, your group is already used 12 minutes. I think I see what is written here. Can we go to next slide, please? Next slide, please.
Okay, thank you. I finished.
Just thanks. Okay. In general, I mean, when we say time, please try to, follow this time because there are a lot of groups and we will be a little strict about this, okay, for next time. Okay.
Sure.
Okay, thanks. I don't have any question. What we have done looks good. Gibran or audience, any question?
No.
Okay, thank you. 32 looks quite good. Thanks. We can continue with 21, project 21, first group. Project 21, any group?
Hello, Abu.
Yep.
I think none of the groups have prepared a presentation.
No presentation.
I have
No,
something
but
quick for
we
20.
can show, but not a PPT presentation, maybe.
Tell
have
me a group
something-
name first.
Oh, that's a good point. I don't know that we've talked about a group name.
You divided into groups or not?
Yes, we have two different groups, but we're presenting as one.
Okay, you will get less grade because of this disorder. Just explain what we have done until now.
Okay.
But please, group names, short, clear,
Okay.
easy to
And
read.
that's okay.
Next time, okay? Also, two separate presentation. I think we said this several times.
Okay,
Okay,
I can do another presentation, second presentation.
Not
Okay,
another,
so
I mean, what you have done as a group.
Yeah, we have done similar things.
So yeah, I can do for one of the groups. And then if Tugba, you want to do for the other group?
Okay, please start.
Or we
One
do
of
one.
you.
Okay, let me start real quick. Let me go ahead and present. Slide. Okay, I'm going to share my screen here. Let me make sure I'm a little less familiar with okay. Let me know if you see this. Do you see the screen?
Yep, please continue.
Okay. Yeah, so just real quickly, the work of this particular project is integration of MIDIT with Classique. So here's the groups that are in there right now. We're grouped into two different groups. There's one group has a few more people than the other, or one extra person. So just a little bit about what we've been doing is working basically on understanding, what error mitigation is. Essentially, quantum error mitigation is a collection of techniques, right, to suppress errors in the algorithms as they're running. And the main point that we wanted to make is that it is not quantum error correction, which is dealing with correction of errors at the hardware level. It does not eradicate the noise. It basically attempts or the techniques attempt to mitigate the noise by making changes to the actual circuit. And so that's why it's also called approximate error correction. And there's some well-known error mitigation techniques, should I say, that we've been studying. There's one called zero noise extrapolation. There's also Clifford data regression, digital dynamic coupling, and then readout error mitigation. Two or three of the ones that we've been concentrating on are ZNE and PEC, which are zero noise extrapolation is one of them. And then also we're looking at dynamic decoupling, digital dynamic decoupling, actually. And these are techniques that are already in MIDIC. And so we're going to see if we can integrate those into Classique. So a little bit about zero noise extrapolation. Any algorithm of choice is run and the expectation values are measured for various values of noise. And then the noise can be tuned by running longer quantum evolution or repetitions of blocks of unitaries and their adjoint unitary folding. All of the measurements are compared and the final noiseless output is measured by extrapolating it to the zero noise limit. The algorithm requires no additional input about the hardware noise or constraints and hence is very simple to use. So this is one of the reasons we're kind of concentrating on some of these, what we would consider low-hanging fruit in ways that we can adjust the circuits as they're developed in Classique and then introduce some minor changes. We'll probably start off, as baby steps, doing some simple changes and then seeing if they have any effect. And then we can move on to either other techniques or expand on the initial changes that we make. There's also probabilistic error cancellation. And there's an explanation there, given a unitary to be implemented along with restrictions from hardware. We can decompose it into a linear sum of implementable noisy operations. There's also some stochastic sampling that occurs. And again, the idea is basically making changes to the circuit after it's synthesized is probably where we'll introduce these steps. If some of you saw during the boot camp, Classique does have some parameters that can be set in regards to some of this error mitigation, and hopefully we're hoping to expound on that. So this is sort of where we introduce error mitigation in MIDIC. As we know, there's a lot of error mitigation to be done. And so, we kind of reduce that in general as discussed. Now, MIDIC is a Python package, and so it's got some methods to utilize that basically come in as functions or calls to the Python library. And some of the ones that, as mentioned, that we're hoping to introduce is ZNE, zero noise extrapolation, digital dynamic decoupling, and probabilistic error correction. So those are the ones that we're targeting right now, and whether we actually focus on one or two will be determined as we start trying to implement it. Now, IBM's Qiskit runtime also offers ZNE and PEC, so we're not too sure how we might try to implement that as well, or utilize some of those features. So instead of calling MIDIC directly, we may also try to call MIDIC and or IBM's Qiskit runtime functions for error correction and possibly compare the two to see if we can improve or not. And then lastly, this is just an indication. Some of the work that the team members have been doing on both groups has been setting up the Classic SDK outside of the Classic UI. So that was introduced in Bootcamp 4, Lesson 4. So we've been utilizing those examples to try to get something up and running. And then several of us have installed the MIDIC library. And so we're going to start working on trying to get those two integrated in some simple fashion. And we want to start off small. We're trying not to start with something too large. Otherwise, we may have trouble looking at it in Classique. or in the SDK, but we also are working on workflows to port the data as we go from working in the SDK into the Classic UI. And that's a conclusion for this presentation. Thank you.
Okay, thank you.
Okay.
Any question?
No.
Okay. So Tuba, will you do a presentation or what Bill said is?
Okay, I can add some points maybe.
Okay, okay.
We are, as two groups, we are now all working together. We are not separated yet, I mean, because we are still learning about the subject. So as long as I read the reports, the team generally focused on the error mitigation concept. As we said, quantum error mitigation has arisen as a practical alternative to quantum error correction because in quantum error correction, the effects, the error is mitigated by spreading the information of one qubit onto an entangled state over several qubits. However, in this NISQ era, the qubits are very valuable, and quantum error correction requires a large overhead since additional qubits are needed. So we can say that this is some kind of a long-term solution. And quantum error mitigation is a near-term solution because these methods are used to extract useful computational output by combining measurement data from multiple samplings of the quantum device. And in our project, we are examining the popular Python toolkit known as MITIC. In this toolkit, several error mitigation techniques are already implemented. Among them, I think we are going to examine zero noise extrapolation and probabilistic error cancellation.
So sorry, Tuba, I think Bill already explained.
Yeah, so
anything adding or?
And we are, I think we all try to implement MITIC and Classic in our Jupyter notebooks or in our Visual Studio. This week, we implemented some basic circuits to learn more about Classic and MITIC. And I think next week, we are going to dive into the subject deeply.
Okay, one suggestion, you will be, and you should be two groups, so just somewhat separate the work. That doesn't mean you can still collaborate, but kind of split the work, and then each group like focus maybe different parts, and also it's easy to evaluate in this way.
Okay.
But as I understand, Bill prepared for everyone this presentation, correct, Bill?
Yes, that's correct. Yeah, it's for the entire set of us because, as mentioned, we were just getting out of the boot camp, and I think we've got good reports up on our GitLab page, and so a lot of the content that was presented today was based on the reports from everybody. We actually utilized some of the content from some GitLab information.
Okay. Also, please find group names and then write to me on like this group.
Okay. Yeah,
this
I just
people,
posted
this group, these people. Okay.
We'll
Thank you.
Thank you.
Thank you. Group 21. So 29 requests. They said they are in hurry. How many groups ready from 29?
So can you hear me?
Yep.
Hi, Abu. So one of the groups is ready.
There is a group name or?
So the thing is, with Project 29, it's not continued anymore because of obviously some difficult situations.
Yep.
But we would just like to present what we have been up to so far, and yeah.
Okay, for how, which people, I mean.
Yeah, I can share the screen.
Okay, please share.
Just a second.
Okay.
Can you see my screen?
Yep.
Yes, so we are one of the groups where it's me, my name is Bhargavi, and Emmanuel, and Mirza, Harsh, Barsos, and Rupesh.
Before starting, there is any people from other group, 29?
I am not sure, actually.
Yeah, I'm here. But we actually didn't formally made any group because the project was going to discontinue. So, yeah.
Currently, these are all active people in 29.
Sorry?
These are the all active students in 29.
This is just half of the group. So
Half of the group.
we would divide it into two groups based on the time zones, and one of the groups
Okay.
has a list of people.
Okay.
And
So, one second. 29 request earlier, Ricardo. This is why we start with 29. But in general, please keep this 2 hours free, okay? In general, for next meetings, just don't put any meeting or try to avoid any meeting during these 2 hours. Okay, 29, please continue.
Okay, hello everyone. So our group was supposed to work on maximizing the quantum approximate optimization algorithm, which is QAOA for short. So for now, I'm just going to elaborate what this algorithm is about and what we have done so far. So QAOA is a heuristic hybrid algorithm, which is used to solve for combinatorial optimization problems. So what are these combinatorial optimization problems? Basically, these are the problems where you have to find the best solution from a finite number of solutions. So for example, traveling salesman is one such problem, or tail assignment problem is another problem where an airline company wants to assign airplanes to different routes in order to maximize their profits. Or another example is the max cut problem, where you have a graph with nodes, and then you want to separate this graph into two sets of nodes, where this cut maximizes the number of edges between these two sets. So this is hybrid algorithm because we measure our quantum circuit and we make use of the classical computer to analyze the results. And then this classical computer updates the parameters and feeds into the quantum part again in order to find the best solution. And this is heuristic because there is no theoretical proof that this algorithm has a quantum speedup. But there are some problems like the max E3 Lin2 problem, where it's actually observed that QAOA performs better than any best known classical algorithm possible. We are not going into details of what this problem is, but QAOA is one of the algorithms which is useful for the current NISQ era. So to briefly explain what this QAOA is, we have a task of maximizing or minimizing a cost function, and we encode this cost function into a Hamiltonian. So this cost function will be the eigenvalue of the corresponding Hamiltonian, and the unitary operator is found by exponentiating this Hamiltonian. So what is the quantum approximate optimization algorithm? Basically, you start your circuit with, let's say, all plus state, and then you evolve your circuit according to the cost Hamiltonian for a finite time, let's say gamma 1, and then it is followed by another time evolution operator that's dependent on a different Hamiltonian called HB. and then this process is repeated several times. So this HP is usually quite simple. It's like a sum of Pauli operators. And the choice of HP will be soon explained. So the idea of the algorithm is you repeat this process several times, and then you have a trial state here, you perform your measurements, and the measurements are analyzed by a classical computer, and you optimize your parameters involved in the circuit, which are gammas and betas, and then you feed these updated parameters here, and then the circuit is repeated several times. So by the results that are obtained are these expectation values, and you may be wondering like why maximizing or minimizing this expectation value will correspond to maximizing or minimizing this cost function. This is because of a concept called adiabatic quantum computation, and which is based on quantum adiabatic theorem. Basically, what it says is that if you have a quantum system where Hamiltonian is going from H1 to H2, and if you slowly evolve the system under certain conditions, the ground state of H1 will go to the ground state of H2. So these type of adiabatic algorithms are implemented and used for optimization problems. So the H1 that is chosen is quite simple, like the sum of Pauli is here. And by slowly evolving, we eventually go to the ground state of H2. So for example, here we chose all plus state, which is like the most like the excited energy states of Pauli operator, or the ground state of minus HB. So by starting with this state and evolving the system with time, we will eventually go to the ground state of H2, where we encode our cost function. So the ground state, all pluses corresponds to H1 here, and the ground state corresponding to the cost function is encoded in H2 here. So with time evolution, we go to our desired solution. This is roughly the idea. Of course, like obviously skipping a lot of details, but just to introduce you to the concept. I made this picture here. And what we did so far is all of us in the group, we installed the Python SDK and worked out a few examples. Tammuz also advised us to implement a real world problem. So some of us did that, and I did the exact cover problem using the quantum approximate optimization algorithm, and the other person in the group did vehicle routing problem, and so on and so forth. Yeah, that's it for now. Thank you very much.
Okay, thank you. So probably we will offer you some other projects.
Yeah.
At least 2 mentors are ready to accept more students. I will share it later. I suppose you wouldn't continue alone, correct?
Sorry?
For example, one group in 31, their project also canceled. They said maybe they can get minimal help and then they can do by themselves. But I think this is not the case for your group.
No, not that I know.
Not really. Okay, it's better. Okay, I will contact you probably tomorrow or after tomorrow, and we will offer me. Thanks overall.
Yeah, thank you very much.
It's good. There is no other group from 29. Okay, 26, first group.
Hi, Abu.
Tanjin?
Yes, we're
Okay.
here.
You can share.
Okay. Hassan, can you share the screen? Hassan?
Yeah, sure.
Yeah, please share.
Usually, please be prepared. You know, there will be several presentations. If you use 2 minutes for each time, you know, then it will be 20 minutes in total.
Okay.
Entangled minds.
Yeah.
26.
Hello, everyone. We're
Minds. Okay. Thank you.
Hello, everyone. We're group Entangled Minds, and we will be presenting the Project 26 Design and Interactive Introduction to Quantum Computing course with Classic. Hassan, please, next slide. Yeah. The objective of our project is to prepare an interactive course based on Classic platform. Here we are focusing on for individuals from different groups and different backgrounds. The course will teach both theoretical and practical implementations of quantum computing basics and quantum algorithms using Classic. Next. For designing this course, we are actually studying for different level of learners from different backgrounds who have basic understanding of quantum computing. The learners who don't have any understanding of quantum computing, and from software development background, for physics background, or non-technical persons. The course will be for designing this course. We are getting understanding now for classic platform, the classic editor, model editor, syntax, and circuit synthesis. Also, we're actually planning something to implement to show the implementations of Grover's algorithm, option pricing, variation quantum, eigensolver, etc. From next slide, Rishi will present.
Yeah, thanks. Yeah, so our plan is to use Classic platform throughout our course as a tool for practical purpose, and we will use it to show how to simulate and execute circuits. And next slide, please. And as preparation, we've gone through several courses in different platforms like LinkedIn Learning and Udemy, and to understand how we can explain our basic concepts in more detail. And we also participated in bootcamp organized by Classic, and there we used Classic ID to implement Grover algorithm, and in Web ID only we experimented with constraints, optimization parameters, and tried how to execute circuits in different vendors like IBM and AWS Bracket. And we also done local setup of Python SDK to locally to locally execute that code so that it runs on Classic platform. So yeah, this is what we learned from Bootcamp. Thanks.
All right, so here's our plan for organizing this course. So we are planning on breaking it down into 5 different stages. So at the very beginning, we will introduce the very foundations of quantum mechanics. This is mainly designed for the audience coming from non-physics backgrounds. So we'll first very briefly introduce the quantum mechanics and this history, and then introduce the key concepts, including superposition, entanglement, and quantum interference. So these are this play a very important role in quantum algorithms. For example, quantum interference manipulates the probabilities of all qubit states and will guide algorithms towards the correct solution by reinforcing good paths and canceling out the bad ones. And so for the potential activities, we will try to use the do some visual demonstrations of quantum states, or maybe even like on a block sphere using the Classic platform. And on the next stage, we will we'll start the introduction to quantum computing based on the principle of quantum mechanics introduced from the first part. So we will compare the differences between classical and quantum computers. One example is we can construct a quantum like a random number generator. So classically and in quantum mechanics, those generators could be like understood in different ways. So in classical generators, you usually like start with an initial value called a seed, and given the same seed, they produce the same sequence of numbers every time, and they're kind of like deterministic and not truly random. Whereas the randomness in quantum random number generator come from the inherent unpredictability of quantum process. So for example, the direction in which a photon will be polarized after passing through a beam splitter is fundamentally random according to quantum mechanics. And this randomness is not based on any classical deterministic process or predictable physical phenomenon. And then we will for the key concepts, we'll introduce what is a qubit, what is a quantum state, and how do we generate a quantum circuit using classic. And building on this, we will start with the introduction, some formal introduction of quantum algorithms. And we will go over some mathematics of the algorithms like quantum Fourier transform, quantum phase estimation, Grover's algorithm, and Shor's algorithm. And we will try to make the whole process as interactive as possible. Then we realize that in real quantum simulation, quantum noise play a very significant part. So we will introduce various quantum hardware platforms, including superconducting qubit, trapped ions, photonic systems, and dive into the concept of quantum noise. We'll go over different kinds of errors that could occur in real quantum device, like depolarizing error, mirroring error, etc. And we will connect the quantum hardware platform with the error that may occur. So for example, in superconducting qubits, there could be decoherence error due to the interactions with the surrounding environment, and there will also be gate errors and readout errors. Whereas in trapped ions, the motion of ions itself can lead to decoherence, and and finally, at the very end, we will try to develop some more advanced examples of quantum simulation, such as the applications of Hamiltonian time evolution simulation, and on say quantum chemistry. And we will hopefully, based on the third and fourth step, we will also discuss the importance of the error correction due to the fragile nature of qubits. So next slide, please. Next slide. All right, yeah. So then, to very briefly conclude, so we are aware that the introduction to quantum information and quantum computing course could be intimidating for the audience coming from different backgrounds. So we will try to make the language as understandable as possible for people from different backgrounds. And this course will provide a theoretical foundation in basic quantum computing as well as quantum algorithms with the classic implementations. So that's basically with our progress so far. So thanks everybody for listening.
Yeah, thanks. It's quite exciting project. We as QWORD also developed a lot of materials and doing a lot of events, and I am also curious about this specific project. It could be also beneficial maybe to QWORD later. Is there any question?
Actually, yeah, just to follow up on Abu's comment as well. So in some sense, I would also recommend not to spend too much time on some of the, or at least, for example, you could use QWORD's tutorials on introductory quantum and let's say Shor's algorithm as a starting step for creating the structure of the tutorials. So for example, the silver workshop already has some material on Shore's algorithm. Q-Bronze already has some material on Grover's algorithm. So in terms of structuring the introduction of the material in terms of how to break down the topic, you could already use those tutorials as guidelines for creating this material. And this should then also provide you more time to spend on, let's say, topics in stage 4 regarding which, let's say, we don't have material as well. And so that should give you more time to work on kind of new stuff as well in that sense.
Okay, yeah, that sounds great. Thank you.
Another question? Probably there is no time for this 5 stages. What would be my comment? So better to focus part, finishable part, and at the end, it's always good to finish it. You can always continue later also. Okay, second group.
Okay, I'm here.
Okay, please share screen, also group name.
Morning for everyone. I'm here. I'm now sharing. So I think it's working now. Okay.
What is the group name?
Our group hasn't decided a name.
I will say educators.
Yeah, maybe educators A, but I will organize to make a name.
Okay,
for
start, Carlo. Thank you.
Well, we are the 26th project, the design and interactive introduction to quantum computing course with Classic. This is the team: Ricardo here, Aswani, Mila, Manjula Gandhi, Denise Vidkova, y Alvaro Rafael Gomez. Well, first, what's the current situation about the quantum programming education? And for sure, maybe it will be useful for keyword courses in future. And for sure, we will use your notebooks. The industry requires physics, quantum programmers, quantum information scientists, and many professionals with a mixed profile. The physics-based approach is useful for training professionals in other sciences. Formal education institutions are not yet prepared for their training, at least in Latin America or underrepresented countries. Companies and other situations have developed a large number of courses covering the topics of quantum computing and quantum information, but with variable level of efficiency and methodology in the pedagogy. How do you say? Well, in the teacher's forms or sense. The word was lost now. And why we will use Classic for this project? Pues for the development of a teaching the methodology that introduced quantum computing, taking advantage of the facilities provided by the Classic in order to make more interactive courses with this platform. This allows students to gain a high command of quantum computing programming algorithms without having to develop low-level code. It will be useful for people who doesn't have professional education, like a career or degree in physics, maybe for high school students. Physical concept must be introduced when necessary and progressively integrated with a quantum programming model. And for our project, we have well-defined first steps, like definition of objectives and target audience, exploration of the Classic IDE, exploration of the Classic SDK, taking a lot of knowledge from the Classic Bootcamp, and many planning group sessions that we are doing in the weeks. Our objectives and target audience are about the target audience is the people who know quantum algorithm background, who doesn't have this quantum technical knowledge. It made a sense of the people who people can learn throughout this interactive course by a course immersive. So if you don't have this background, you can learn or understand the course by itself. So the course should be served for people from the scientific field and from the computer science field too. And more for people who are immersed in these fields in the teaching in the teaching wave. Well, about the objectives, we have enabled newcomers to get into the field quickly with a good understand the basics algorithm using classic SDK and IDE. About the content, it will be really useful, a lot of notebooks and tutorials that made QWord and other communities, like in the case of Spanish communities, Quantum Kipu. Well, we have defined the content of state preparation, Graber's algorithm, Simon algorithm, quantum Fourier transform, and quantum phase estimation. Sorry. Well, about exploring the tool at the Classic Bootcamp, the Classic platforms allows the automatic generation of quantum code, but also provides access to the low-level code generated, which can be used in the scope of the course to present to the student key ideas about quantum algorithms. The general user interface is quite simple for computing science people, and the graphical user interface for circuit visualization is very easy to use. Our main challenges that we found in these 2 weeks are establish the minimum necessary content on the use of the Classic platform, find a way to transmit quantum programming concepts within the framework of the Classic platform, ensure the student distinguishes the essence of each quantum algorithm independently of the characteristics of the platform. And well, people can decide, no, if they can introduce more in the characteristics on the platform or in the algorithms, and develop interactive tools with the framework of the Classic platform that facilitate the transmission of knowledge about quantum algorithms. Thank you.
Yeah, thanks, Ricardo. Okay. Yeah, these 2 projects, these 2 groups, yeah, exciting. So any question or comments for the educators? Okay, thanks, Ricardo. Now group 27. Also, in general, it will be good if you open your cameras when you are presenting, as Ricardo did. 27? Project 27?
Hello.
Okay, you can share.
Okay.
Pedagogical, Ricardo. Jonathan or Jonathan?
Can you see my screen?
Synapse. Okay, you can start. Thank you.
Sorry. Okay. Can you hear me?
Yes, you can start.
Okay. Hello, everyone. My name is Jonathan Jauja. I'm from Peru. I am a final physics student here. Today I'm going to talk about our first presentation, the first part of our project, the quantum neural network algorithm implementation. It's the 27 project. Our group is the Synapse. So I would like to start with a little presentation with a little introduction to quantum machine learning, because this project is focused on one of these sub areas of the quantum machine learning, when we use classical data like images or Excel files, and we use quantum algorithms or a mix of a classical and a quantum algorithms like QNN. So this presentation is to present the classical neural network model, because I think it's so important understand so well this model to then implement the quantum version. So what are neural networks? So basically, can you hear me?
Yes, everything is all right.
Okay.
Hello.
Yeah, can you hear me?
Yes, we hear you. You can hear us.
Okay. Okay, neural networks inspired by the human brain are computational models composed of interconnected nodes. These networks find practical applications in our every lives, from recognizing speech to analyzing images and understanding text, between other important applications that we probably use. And we can see that the neural networks have layers. We have an input layer, multiple hidden layers, an output layer, and each layer have neurons, and each neurons have associated weights, and these weights are so important because these weights will change during the training process until they are the best are possible. So how this neural network works? We need to know that each neuron that we could see in the last slide, the output of each neuron can be calculated using this formula. That is, we need to calculate the inner product between the weights and the input data. So after that, we need to apply a activation function to avoid the linearity of the model. So basically, sorry. Neural network in the neural network training involves an iterative process. The algorithm initially says random weights and biases, iterating through the training dataset for a specific number of times. For each training example, the network calculates the break output. The loss is then calculated, where the loss is representing the difference between the predicted and actual values. Then using the backpropagation algorithm, our algorithm adjusts the weights and the biases using gradient descent, aiming to minimize the loss. This process continues and continues until all the training examples have been processed. So it's important to understand how the neural network works, because the quantum neural networks, in the quantum neural networks, we will use several steps of the classical part. That is to say, in quantum neural network have classical part and quantum part. The quantum part is related to the or correspond to calculate or to implement the quantum layers, and after that it's all classical. So the way that I understand it, it's basically the quantum part will be encoded only within the quantum layers of the neural network. The quantum layer receive and return classical values. That all the quantum processing is internal. That is the way I could understand the moment. So we can implement a quantum neural network using instead of these layers, quantum layers, or we can mix between classical and quantum. That's all. Thanks.
Thanks. Are you alone, Jonathan? Are you working alone, or there are other people? You are muted, Jonathan, if you are talking. Your microphone is off now.
Oh, I'm sorry. No,
No problem.
I forgot to put the members of my team.
Your team knows like neural network, yes, classical neural network.
Sure. My team
For
is to onboard to
QNN, for
Alex.
quantum neural network, you don't have any knowledge at the moment, correct? For quantum neural network, you currently don't know how it works.
Oh, a little bit. I am studying this part now.
What about rest? The other members?
I don't exactly. I don't know if they
you
are studying this part.
You prepared alone this presentation?
Yes, I suppose the next presentation we will my team members present.
Okay, you had a meeting as a team or not as a group?
Yes, it's a group. QCourse551-1.
So you met and you discussed also, correct?
Yes, we have a group in Slack. We create a Slack group.
Okay.
Sure. I'm sorry, I forgot to put the members. The members are
okay. But currently, I didn't get what is your plan. So next time it would be better what you have done and what will be the next. Okay.
Okay.
Okay. Thank you. And next group, please, from 27. Is there any group? 27? Any other group? Okay, 31. Which group will go first?
I can go first. My name is Crystal.
Crystal.
Turn on my camera.
David's group is different, correct?
David is the same group as mine.
And you also want to continue similar to David, or?
Yes.
So this 31 would like to stay with little help, but they need some mentors just to check this individual.
Yes.
Okay, good luck. It's nice to hear also such challenge. Okay, you can share, and also I need a group name from your side.
Sure. So, hi,
yes,
my name is Crystal, and I'm representing Project 31, which is working on quantum backtracking implementation. Our team name is VZKD, which is short for Very Zero Knowledge Decision, because we hope to acquire knowledge along our journey. And our team members are Vansh, Zihan, David, and myself with mentor or Samimi. So our motivation for this project is something like, given a constraint, find a set of practical solutions. Specifically, we're dealing with problems that have certain sets of solutions, such as that of the Boolean satisfiability problem and the graph coloring problem. So they're often computationally difficult, having even exponential time complexity, but using quantum computing, we can speed this up. So here on the right-hand side is a color of an example of the 4-color theorem, in which the goal is to color a map using only n number of colors. So what does n have to be for this to work? As it turns out, n must be minimally 4. So these sorts of problems are useful for things like scheduling or routing in maps, allocating memory in compilers, network routing, artificial intelligence, and security. So our progress as a group so far has involved taking the classic bootcamp, in which we got hands-on experience in parameters and repetition for Grover search, dealing with high-level functional design, hardware constraints, and in using the Python SDK. So we were also assigned 2 papers to reason about. The first is on speed up of backtracking, which is by Montanaro, and the second is on backtracking implementation, which is by Martial and Rameau, as well as given the task of completing the bootcamp. So our subsequent tasks have involved deciding on constraint satisfaction problems, which I'll call CSP from now on, to solve and to generate test data, implementing classical and quantum backtracking using the SDK, and improving upon the quantum algorithms. And finally, our paper should wrap up our improvements and findings. So classical backtracking, according to the paper by Montanaro, is modeled by predicate logic. So if we have X, an assignment in some subspace of D, or star, a partial assignment, we can use our predicate P to map our values in our subspace D to either false, true, or unsat. So we start with a set of predicates such that for each heuristic H that maps D to set 1 through N, we return the following index and move forward or recurse through a tree using a recursive call, which is called BT, starting with all stars. So at the end of the call, when we have determined whether we have an X or a star, this tells us that P of X is true, where we find a solution, P of X, where we find a solution, but it is false, or P of X equals unsat or indeterminate if the solution is not determinable. So what does this mean? So here we have a tree where we want to find solutions that will give us 4. So we can go recursively down each branch and find that in the 2 branch, we get 2 + 1 + 1 = 4, and 2 + 1 + 3 = 4. So the first is true and the second is false. And we can also do this for the 1 branch. So if we can't find a solution at all, we can claim unsat. And such a problem would be something like prove true and not true. And as we can see in the diagram in algorithm 1 of the Montanaro paper, we start with our predicate P that maps D to either true, false, or unsat here. And our heuristic H tells us what clause to choose next. And then by picking an arbitrary variable in the shortest clause at the time of our tree, having made a previous selection, which gives us a smaller set of assignments. And this is a variant of the DPLL algorithm, which is discussed in the paper and is often used in SAT solvers. So H maps D from 1 through N and returns BT of star to the nth power. And the branch returns when the output is true or false and continues a recursive call, which is called BT of Y, otherwise. So some of the background techniques used or mentioned and speedups in the paper are from Aronson and Ambianis, who don't use a quantum walk, but assume that an input graph is known. So using branch and bound, they acquire a speedup, which is something Montanaro uses. Bellows thinks about a graph as an electrical circuit where we have a random walk from the root of the tree. And in the work of Bellows, we assume that the input graph is not known in advance because it is defined by the backtracking algorithm, but uses resistance between the initial vertex and a set of marked vertices. In terms of these marked vertices, Montanaro uses a method to check that some predicate P star X is true. So if it is, they run this algorithm too, which is in the paper, and this gives us a speedup based on some marked indices. And a marked vertex can be some internal node within the tree. Finally, nested searching is used, and this applies a Grover search within a subspace spanned by a vertex in the tree and its children across many vertices and levels simultaneously. So Montanaro notes that our tree may be unbalanced, so we can't expect equal weight on the left and the right sides in terms of the leaves of the tree. So the extension of Beloves by Montanaro uses properties of the eigenvectors, which are usually denoted lambda 1 through lambda n of the random walk and of the mixing time to extend the work of Beloves. So the mixing time is the time it takes for a random walk to arrive at its stationary distribution. Usually we sample from this probability distribution, and it gives us information about an event's likelihood. So our eigenvector or spectral decomposition can give us information about how connected our nodes are, which can tell us something about how we can partition our graph, and therefore how quickly we can find solutions. And finally, branch and bound, which is discussed as a method of speed up in the Montanaro paper, is a form of optimization in combinatorial problems, which breaks them down into sub-problems by using methods where we can reduce the number of problems by eliminating problems with no solution. So we can think of this as a tree and pruning the tree. So Montanaro notes that in quantum complexity, we don't necessarily need to know the length of the tree, which is important in backtracking, where we often don't know the length of the walk or the tree, and they leverage this knowledge in their paper to get a time complexity of O square root of T of n, and Martial and Rameau show an implementation of Montanaro's backtracking algorithm that uses less data qubits and CSP problems. So they achieve this by using phase estimation and diffusion operators, where we have a diffusion operator which flips n amplitudes about the mean. So the largest overhead in Montanaro's work is the heuristic implementation H, and Martial and Rameau use static variable ordering, or SVO, which uses some kind of pre-computation and doesn't require dynamic variable ordering, or DVO, which is a parameter that we want to minimize. So Martial and Rameau require a quantum counter and present their results on the graph coloring and SAT problems. So their implementation involves the use of this ancella registers, H sub anc and H sub children, a basis state of ket L and V sub 1 with swapping. And this operation, which is shown here, so they make use of quantum operations versus the Montanaro paper. So they also make use of the maximum cardinality, the maximum degree, and maximum width of the tree. So since they've looked at certain problems, such as the four-color theorem and the traveling salesman problem, our group is going to look at similar ones. Our initial constraint problem is that of Sudoku, which we've already started coding up, where we start with a brute force implementation and improve this implementation using Classic, the SDK in particular, and observe and improve the time complexity. So we've also worked on white box fuzzing for cybersecurity, which is David's working on that. And I want to note that in Montanaro's discussion of their paper, they also mention a potential problem of calculating the number of solutions for the problem, which is something that we could also look at as a corollary problem. So other problems involve the rat in a maze problem, which is the one to the right, and the Hamiltonian cycle problem to the left, where the goal is to find a cycle where, except for the first node, each node in the cycle is only traversed once. And what we hope to do is to open source our code and submit to a manuscript to QCE, which has a deadline of April to June next year. So our next steps are learning more about the algorithms, parameters for speed up, and overheads of our algorithm, and working on a code implementation, as well as collecting a set of applicable problems of solving. And so these are the resources that we looked at. This is just a subsection. We have many more. Thank you.
Yeah, very, very impressive. As you said, you did a lot of work. One question, you had this background, or you just read this paper in these 2 weeks?
So we had a mix of persons. So within Zihan has a math, physics, computer science background, quantum background. David also has quantum background. Vansh also has quantum background. I don't have as much of a quantum background, but I have cryptography and I've done graph theory. So reading the paper was very approachable in terms for all combined. This is a joint effort and everybody's works really hard. So yeah.
Because these papers are not easy, I know. These fellows and Binance, I am working in that group also. I mean, they are kind of advanced topics, so congratulations. So somewhat we combine some strong group together.
Thank you.
Yeah, you should continue, I agree. So you already have some aims, some conferences, so that's already good. Okay, I will look for one mentor checking your individual reports, it seems you will be able to just work by yourself, self-motivated. Thanks. Any question or comments for this group? Okay. So there is another group from 31 or?
Yes.
And you will present as well?
Yeah. Okay. Okay, I'll be sharing my
Please share
screen. I'm sorry for the inconvenience. Could you see my screen?
It's cell phone, I guess.
Yeah, my laptop is not functioning today. It's broken.
Okay.
So
Do you have a group
sorry
name?
for the inconvenience.
No problem. Do you have a group name?
And unfortunately not, because most of the group are inactive. So
How many students are active?
um,
Only one? I hope not.
there were one on. Yeah, only one.
Only you are active. In your
Yeah,
group,
there was another
you are the
person,
alone.
but he started like 2 days ago. Yeah.
2 people. And you want to change your group, yeah? Because there is no mentor now for 31.
Yes.
Okay. Okay, thank you. Then floor is yours. You can explain what you have. Thank you.
Yeah. So our project is implementing quantum backtracking. So last week task was finishing classic bootcamp and reading 2 papers for quantum backtracking. First one was quantum walk speedup, and other one is practical implementation for quantum backtracking. And another task was to decide what type of problem we are going to use quantum backtracking. So in the classic bootcamp, we have like 4 assignments. The first one was Grover search, and then optimizing the circuit. The 2 other problems, and the final one was about optimization. So our problem is quantum backtracking. So in backtracking, we are trying to find a solution for some problem based on some constraint, like a CSP problem. So in quantum backtracking, we're like we design our problem as a tree, and we're trying to explore which part of tree to continue at if we're going to find a solution. Else we go back to the part where we might explore another branch of the tree. So this is a classical backtrack, and we're currently looking at quantum backtracking to have like a speed up. So one of the problem is constraints and CSP constraint satisfaction problem, where we have like a problem of n variables, and we're trying to find a combination of the variable, given that we have a set of constraints that should follow. An example for it is like map coloring, Sudoku, or crossword. So in map coloring, you're trying to color each vertices such that no adjacent vertices have the same color. This is one of type problem CSP. So our target is to have colors, but our constraints that no adjacent vertices have the same color. At Sudoku, we are trying to get the numbers, but we have like a constraint where each row have a unique numbers, each column have a unique number, each I think box have like numbers from 1 to 9 and should not be repeated. So in usually to solve the CSP problem, we use backtracking. We're trying to have like an initial set of a problem, and we're trying to solve it as a graph. So each node is like a possible solution, and then you expand it more. If you find like one node is not satisfying the condition, you go at the level above it and explore another branch. So backtracking is it's like an improved version of brute force solutions. So current literature advise like using a quantum backtracking, which will have like a speed up. So one of them was through quantum walk. So the problem is like we're going to have a tree and we're going to apply quantum algorithm, but when we applying it, we are trying to have a speed up where we're trying to traverse a tree, like finding nodes which might have which might satisfy the constraint we have. So as an input, we have like the quantum walk operator, which is, and the tree we are going an input tree, but they said like it's not a deterministic, and how much we are going to explore the depths of the tree. So at first we apply like a quantum phase estimation because we are trying to mark each node if it is possible to if it's possible to satisfy or not. And we use a quantum phase estimation, and if the eigenvalue is 1, then we've said like this branch satisfy our constraint, we're going to continue. If not, we just explore another nodes. And one of the parameters is the depth of the tree, because the depth could grow, could grow exponentially according to the problem. So an input is like how much we're going at depths we're going to explore in the tree. And the speed up, they did have like O square root T by D, like the number of nodes we have and the depth. And they said that, like, they have a low margin of error where there might be a solution, but the algorithm could not detect it since it doesn't explore the full tree. So as an initial problem, we thought of using like solving using Sudoku or N Queen's problem as an initial, and we could extend it like to solve a crossword problem or rat maze or Hamiltonian cycle. So the next task is to finalize which problem we're going to use and to start implementing the brute force and backtracking classical solution, and to further dive deep into the algorithm and to understand what each hyperparameter is used and how it could be optimized. Yeah, so thank you.
Okay, thanks, Ram. You said there is another active person recently appeared. What is name?
I think it's I don't remember his name.
You don't remember? Okay.
Yeah.
Okay. Thanks. I hope, as I told, we will offer probably another project, and I hope it will be convenient for you.
Yeah.
Okay. Thanks for all. If anything is missing, any group, just let me know now. I see already 10 people also left. I think overall it is good. We still have a few logistic issues to be solved, and I hope in 2 weeks we can like fully continue. I think overall all groups like just got the idea and they are ready to work. It's nice to see this. I don't know if you have any question, you can ask me, and from November 1st we will also start to exclude inactive members from the courses. Okay, after 2 weeks we will just check if there is no individual progress reports, etc., we will exclude these students from the course. Gibran, you have any comment before closing?
No, it was just good. I agree. Lots of good presentations.
Overall, it's very good. Yeah, thanks for all of you. Just keep on the track. This is a nice opportunity. I hope all the projects will continue until end. The ones not cancelled yet, I hope all will continue, and we will have a successful end of semester, I hope. Okay, as I see also there is no question. Thanks for today.